So the last speaker of the session is one of the organizers of the conference. Fan is going to tell us about rhombohedral magic and Allan's quantum pencils.
Okay, so first of all, thank you everyone for coming here. So I can come here too. This talk is going to be very brief because we have to move out of the room at 5 p.m. So I do want to mention to you, if you feel like the talk is interesting, go to the March meeting tutorial. So my collaborator Longzhi and me will be the only speaker there. We are going to talk about this for 4 hours. Okay. Okay, so I didn't realize that my first part will be related to talk about Greg. And personally, I came here in 2006 with a beautiful dream, try to understand something called a theory of everything. So quickly I realized that this is really against something in our own culture. That is this. Okay, so because this is really risky, it might end up with a theory of nothing. So I have to do a theory of something. Okay, great. So that is it because I choose to work with Allan, and I feel like Allan really is a role model in terms of this. Okay, so I'm not sure Chen Yu is here, so Chen is going to be responsible to explain what is this to Allan. Okay. Okay. So what happened in between this is that in starting from 2007, I started to wonder, in the big building, except 13th floor. Okay, so everyone knows 13th floor is where those condensed matter physics people, surface. I try to avoid that. I don't want to work on condensed matter physics for some reason, and but I have to take Allan's course. He, at that time, people complain, other teachers teaching, STEMAC. Allan becomes our teacher, so it is required. So I didn't do well in the course. It's very untypical. So at the end of semester, Allan started to discuss Thouless transition. Okay, that's the time I feel like, oh, condensed matter physics is really interesting. I want to work with this. I want to work with Allan. Then I emailed Allan. I said, Allan, this is Fan Zhang, blah blah blah. I didn't do well in your class, but I still want to. I still want to join your group. So Allan replied, yes, indeed, you didn't do well in my class. So I talked to my friends in Dr. Demkov's group, in Chen Yu's group, and they told me, Fan, don't worry. Allan is such a nice person. He's not going to say no to students. Never. Just keep talking to him. Pretend to be your English not that good. Okay, I did that. I did that. So what happened in December is in the quantum we took a quantum field theory, and I had a grade which is over 100. It's 104, and then my friend suggests me, Fan, carry that exam papers to Allan. He's going to take you. I did that, and Allan actually took me, and then told me, Fan, maybe you can work on strongly correlated physics. I realized, oh, what is that? What is that? But anyway, so that day turns out is my birthday. Okay, so thank you, Allan, for taking me. Okay, so that is my thesis dissertation with Allan is basically electronic correlations in field layer graphing. So basically, there is a take-home message today. That is what Allan wrote in one of our papers. That is on the bottom of page 1. He said, we believe that this system is likely to be a fertile ground for new physics. So I think this is a very precise description of that system, as many of you will agree. Okay, so what is the rhombohedral graphing system? So this is pretty simple. It's like a quasi-Sushver-Higgs model. So think about in each layer we have A and B sublattices. So there is an interlayer coupling. The Lewis layer interlayer coupling is between the second layer B and the first layer A. Okay, because they are directly on top of each other. The energy scale is 400 millielectron volt. Okay, so because of the dimerization, so this system becomes reduced into a two-band model, right? You always have a low energy side A1 and the B3, right? A1, Bn. This kind of bilayer system. One low energy sublattice on top layer, one low energy sublattice on bottom layer. And the hopping between this is kind of a, n step. Depends on, it's n, what number of n. Okay, so in this three-layer system, hopping from A1 to B3. So first step is from A1 to this dimer, the first dimer to second dimer, and then to B3, three steps. So that's why in tri-layer, this dispersion is P to the third, okay, P to the third. Of course, other, dimerizer states will get out with energy scale like roughly 1 electron volt. Okay, so the Hamiltonian is very interesting. Okay, so because of this, physics just explained to you, the dispersion is P to the n. Okay, and we all know that in single layer graphene there is this kind of a Dirac point with barrier phase pi. So inversion symmetry, time versus symmetry, and the chiral symmetry protects that Whiting number 1. And because this hopping doesn't break the symmetry, so therefore this Whiting number has to be preserved for n-layer system. So we have this Whiting number n, barrier phase n pi for this n-layer behavioral graphene system. Okay, so it turns out, so if you do if you calculate the density state, so the density state will be 0 at Dirac point in single layer graphene, is a constant in bilayer graphene, and becomes divergent for n bigger than 2 systems. Okay, so if I translate that into theory language, right? If we do a kind of perturbative RG calculation and using constant interaction, that will say in n equal to 2 bilayer system, the interaction is going to be marginally relevant. Okay, so it's really strong. And in n bigger than 2 system, the interaction is already relevant at a tree level. Okay, so turns out, so because of this interaction, there is a very strong interacting, chiral symmetry breakup. So the result, is that these two bands doesn't like each other. They don't want to kiss each other. There will be a gap opening right here. Okay, so this is also the first time we show the Dirac mass, projection in this beautiful system. And if we only look at single layer, single valley, single valley, single spin, the electrons will tend to polarize in one of the 2 layers. Okay, so they are polarized per flavor. Okay, so this is also the first time in graphene system orbital magnetization shows up. So Allan did break my heart once. So I didn't tell him. So when people talk about orbital magnetization in twist bilayer graphene system, so this really is similar to this. And I think in Allan's first few papers he never mentioned this. But I mean, Philip mentioned email people about citation. I didn't do that. I just say maybe Allan is too busy. So turns out after a couple of years, Dr. Kenshi showed me some document for some other reasons. I read what Allan wrote, for some other stuff. He said, the correlated insulator in twist bilayer graphene system, is very similar to this type of physics. Yeah. Okay. So that time I was very happy. Okay. So this is the first, experimental data shown by, Jeannie Lau and Mark Bockrath in the audience. Okay. So basically, transport, spectroscopy measurement, at a zero magnetic field, 0 charge density, 0 electric field. There is kind of gap opening. Okay, right here. And later on, during pandemic, the Manchester group did a more systematic study about this rubber-hadron system, basically showing for hexagonal stack system and the rubber-hadron system, there is a very contrasting behavior. So for hexagonal graphene system, so the resistance doesn't depend on the density and a perpendicular electric field too much. But however, there is a highly resistive phase at a charge neutrality at 0 density, 0 magnetic field, 0 electric field. That is a kind of a layer antiferro phase. And of course, we can use electric field to kill that phase and open another gap phase, which is a 40-layer polarizer phase, right? Basically, you move all the electrons to one layer. Okay. So let's try to understand this. Because of interactions, there will be gap opening at the band touching point. So graphing system has two values. We have to ask the sign of the mass terms, right? So plus sign or minus sign. So it turns out there are two possibilities if we consider two values. So it turns out, so in the first possibility, so all the electrons will go to the, let's say, top layer or bottom layer. So all the parameter will couple the electric field. Okay. In the second case, so the value k goes to top layer, value k prime goes to the bottom layer. That is a ferromagnetic phase, and it's kind of like a Haldane phase, driven by interaction. So that all the parameters can couple with magnetic field. Okay. So if there are also two spins, right? If we consider spin, in total there will be 5 different states. Okay. So I'm going to talk about a particular one, which is the most interesting, and which is realized recently in experiment. So what about if one spin that can have this ferroelectric order, and the other spin has this ferromagnetic order? So that can combine together, it will become this phase. It's kind of like a partially layer polarized, right? So once we realize that there is a chain number inherited from this phase, this spin, then following the Strela formula, so density can also be a tuning parameter of the system. Okay, so combining the electric field, magnetic field, and the density, so actually this very special phase, quantum alarms Hall state, has a is kind of like an octet, 8 of them. Okay, because we can use the strip parameter to tune that. And starting from there, I start to talk about this phase with different groups, including Ginny and Thomas Weiss at Germany, and Longzhu at MIT. And it took like 10 years, and then finally people realized this kind of phase in a rubber hydrography in 5 layers. There are also experimental data in 4 layers as well. Okay, so at charge neutrality, there is a gap phase. It's a layer antiferro phase, and if you add electric field to the system, that layer balance state is going to be killed, and a very large electric field, there's a fully layer polarized phase. Okay, in between there is this partially layer polarized phase. Okay, so and this phase turns out has this a chain number 5 because it's a 5-layer system. Okay, and this is shows how good the quantization of the Hall resistance in that system. Okay, it's fully quantized. Okay, so the magic of the MIT experiment is that besides hexacycloball nitride encapsulated device, they also add a 1-layer TMD to the system. So that TMD can introduce something interesting. Okay, so at this point I should mention that why the ground state is layer antiferro phase. That is because the value degeneracy is very hard to be broken by interactions. So this has been shown in this beautiful paper. I remember the reviewer asked us whether you're indeed including so many interacting parameters in your system, which is unbelievable. Okay, so but the TMD, this TMD can introduce something called Eisen-spinor coupling, tau Z SZ, which breaks spin and value degeneracy of system. So that is kind of ingredient added to the experiment. So I should mention, this is also first introduced by Allan and Hua Chen, his former postdoc, with the collaborator, I believe, Mapilgo, yeah, in this paper. Okay, so with that, I do want to tell Allan, Allan told me, quite a few times, as a theorist, the best moment is when a experimental laser locker door. So that did happen, quite a lot nowadays. Okay, so it's still same problem. So in the past couple of years, people talk about tracer biographic superconductivity. The bands are really flat. Cooper pair has very slow velocity. How can they superconduct? So it turns out, people in the audience, Enrico Rossi, Andrei Borovic, they had a theory talk about, this quantum geometry will give a kind of strong contribution to the superfluid weight, and therefore, superconductivity is rescued. And my collaborator Ginny and Mark, they did a very beautiful experiment, kind of demonstrate that. And more recently, Phillips group and the Pavlov's group, they have very direct measurement of superfluid density. Okay, so that kind of collective effort remind me, there's also a geometric perspective of Allan about our own problem. So remember I show you the widening number is very high for n-layer system, right? So that is kind of like a layer pseudo-spin widening within momentum space. So Allan once said, okay, look at the kind of energy, that's like a kind of a big vortex. It costs a lot of energy. So what about interaction driving all of them out of the plane? That can make the energy, relate. Okay. So that is Allan's initial perspective of this problem. We never, get a chance to figure this out in detail. So I talked to Allan, a couple of years ago, and Allan, kind of instructed me, we should calculate finite momentum, accessibility of the system, and indeed, my student in the Tianyi, where's Tianyi? Okay, he's here. Okay, he did the calculation. It shows the result is indeed very beautiful. So the zero momentum term of the accessibility is actually negative. That means, the order state is paramagnetic, with respect to the electric field. Electric field can kill that state, okay? So, but however, the finite momentum term is kind of positive, and with a lower bound. The lower bound is given by the value chain number, okay? Basically, is half of the widening number of the long interacting system. So that basically says, the chiral symmetry breaking, ground state is kind of robust to quantum fluctuations. Okay, so if we fit that into Ginsburg-Landau theory, we'll be able to show the TC is actually enhanced, and that state is quite stable. That's why people observe this charge neutrality gap phase in many different devices. So we are going to have a paper with Allan. So this is also a tradition in his group, to put this XXXX in the archive paper. Okay, so it's not my intention to do that. It's just happening this way. So this also reminds me, I must be a very good student of Allan. So look, I'm still working on the first problem Allan gave to me. So at same time, I also feel like maybe I'm the worst student. I haven't finished my first project. Okay, great. So okay, in the remaining 2 minutes, I'm just quickly go through the doped case. Okay, so we just mentioned the physics at charge neutrality. Now when we start to talk doped system, so I have been a little bit cheating because we only add a Lewis-Laber interlayer hopping. We haven't talked about the other hoppings, interlayer hoppings. When we add that, they don't break chiral symmetry, they don't break inversion symmetry, time inversion symmetry. So this kind of widening remains. That basically splits the band touching point into multiple Dirac points. And when those Dirac points, Dirac cone merge, so one half singularity emerges. So this is kind of some picture in bilayer system. So the take-home message is really at a finite doping case, there is a low density saddle points and one half singularity in this system. And they can be pushed to higher and higher density if you make the perpendicular electric field higher and higher. Okay, so many of you might work on Kagome metal. So there, at a quarter failing or three-quarter failing, you will have this one half singularity. But here is really at a very, very low density, and they can be tuned by electric field. Okay, so this is what Allan wrote in that paper. Now let's take a look, how that's verified by experiments nowadays. So if we starting from the high density and lower densities, okay, we'll see this 4 iso spin, okay, long interacting metal becomes kind of stoner magnets. So the spin value 4 flavors, right? So not all of them will appear at the Fermi energy. So we'll have this half metal, 2 isospin flavors appear at Fermi energy. If you lower the density, you get a 1 appear the Fermi energy. Of course, if you further lower the density, there is kind of like a weaker crystal regime, okay, right here. And what's interesting is superconductivity also appear in this system. Many ways I do want to mention here in quarter metal is a spin polarized, the valley polarized phase. They can still have a superconductivity, right? So obviously that's a periodic wave, and we do have something about that, but I'm not going to talk about that today. So I'm happy to discuss with any of you later. Okay, so one thing I do want to mention about this weaker crystal is that is also I found a paper to explain some experimental data. I have to discuss with Allan to get his insight. He helped me propose a phase called anomalous Hall crystal phase. So that was first proposed in this paper to explain the experimental data. And nowadays, discussion about this special phase is everywhere. Okay, thanks, Allan. And of course, we can also add a TMD to the system, right? So the similar physics also occur when the system has modulated interaction strength and spiral coupling. Okay, so it's pretty similar. So I do want to mention as we show in this a paper with the MIT group. So once you add a TMD, the 3/4 metal phase do appear. Okay, so 3 isospin flavors appear at Fermi energy. Okay, it's also a stoner magnets. So besides that, there's one message I think is not in the community. People always think maybe we add TMD that can always enhance superconductivity. But it turns out that is not completely true, because there are also cases and the TMD does reduce superconductivity. Okay, the details in this paper. So of course we can also add more ray to the system by making the graphene layer align with hexagonal nitride. So therefore we can see this beautiful correlated insulator phase at nucleus 1, nucleus 2, nucleus 3 at the Moray site. Okay, at the interface far away from the Moray, actually one can the interquantum almost Hall state is also observed. So in between there are fractional quantum almost Hall state also observed. Okay, so okay, so there is also some of the paper try to explain why there is a fractional quantum almost Hall phase in this case. So this is done with Zhang and Xiao. Where's Xiao? Okay, talk to him. Okay, so my own student Tianyi and Longzhi student Tonghang Han helped me draw this beautiful diagram. So credit to them. Also, they working really hard to get this very rich phase diagram. Okay, so just an overview of the talks of the day. I think certainly people agree we have a discrete nodes in graphene system, which is A layer, B layer, C layer, and there is also a continuous node that is twist angle theta. And we can also add TMD hexagonal nitride to the system to enrich the physics. So Allan tells us we can always write them vertically. So there are beautiful melodies of many body physics in graphene system. Okay, and of course some of you said maybe we'll have another celebration for Allan in a few years. So I'll be very happy to do that. But there's one condition. Do bring Allan a gift. Okay, that gift is a quantum pencil. So what is that? That is a rubber-hydro graphene crystal. Okay, try to make that happen. I know all of you have experimental collaborators. They can grow fancy crystals, but we don't have that yet. Think about that. If we have a rubber-hydro graphene crystal, so that would definitely benefit the community, right? And just for a knowledge backup, and right now in natural graphite and the rubber-hydro stacking is kind of defect. We really want to make the hexagonal phase to be a defect. Okay, so this is really the end of my talk. I think what Allan's work at this university is really a testimony to this brand message of the university. What starts here changes the world. Okay, with that, I really would like to thank our collaborators. Thank you.